Having a strong foundation in part-whole relationships is critical to children's mathematical development. It has the potential to influence them for years to come in terms of their competency in mathematics. That's because you need this foundation in order to develop conceptual understanding of all the operations, and it's a critical component of number sense. In fact, even though the term part-whole relations is not found directly in the Common Core language, it undergirds essentially all of the standards in the kindergarten Common Core under the operations and algebraic thinking domain. The cluster title even refers to this or alludes to this idea by understanding addition as putting together and adding to. There's your composing, and understanding subtraction as taking part and taking from decomposing. So this idea of pulling numbers apart and putting them back together and understanding the relationships of all the parts is embedded in this kind of understanding. And we're going to primarily be looking at Standard 3 with some references to other standards. And Standard 3 is looking specifically at decomposing numbers 10 and lower. So what are part-whole relations? Well, essentially, it is the relationship between a whole or total quantity and the parts that it can be partitioned into. So you can pull a whole or a total apart into two smaller parts or add-ins. The Common Core authors have indicated that the word total is preferable to the word sum because of the fact that the word sum has more than one meaning. I can say I have some chickens, or the sum of these two numbers is 5. For that reason, they say total is probably a better term to use with young children. The add-ins would be the proper mathematical term for the parts, but the Common Core authors have indicated that at this point you can choose a more user-friendly term in kindergarten for those parts. You might refer to them as number partners. The Common Core authors have indicated partner would be an acceptable word to use there. Now, initially, this capacity to pull numbers apart and put them back together is actually quite physical. So early in the school year, when they're working with a quantity of 5, to learn the decompositions of 5 will require them to have 5 counters and to move them in different ways, showing how they can be partitioned. But later, that kind of concept is going to be internalized so that a child can think in their mind that 5 could be partitioned into a 1 and a 4, or a 2 and a 3, or a 3 and a 2, or a 4 and a 1, or 5 and nothing. And that understanding is foundational towards subsequent learning. There are a number of first grade standards that are entirely dependent on children getting this capacity to decompose numbers in kindergarten. It not only will support the first grade standards, but it also supports some of the other kindergarten standards as well. So previously we talked about Standard 2 in the Operations and Algebraic Thinking domain, which discussed solving different types of addition and subtraction word problems. And we found out that in the progressions document, the authors have specifically stated the kind of problems that kindergartners need to be able to solve. And one of those problem types is a put-together take-apart with both add-ins unknown. In this case, you only know the total or the whole number, and you're going to try to find all the different kinds of combinations that it can be decomposed into. So obviously, this particular problem type, even though it's part of Standard 2, is how you go about Standard 3 in many ways through these both add-in and unknown problems. They lend themselves to this idea. I thought I'd show you a couple of pictures from some curriculum of what it might look like to have some tasks that decompose numbers. And even though these have little in the way of words, you can make up word stories about them that are very similar to the part-whole problems that we just saw here with both add-ins and unknown. So in this case, there are sheep. How many sheep are there? Okay, so you can establish that you have 6 sheep. I have 6 sheep. Some are blue and some are green. How many blue sheep could I have, and how many green sheep might I have? Essentially, that's the exact same kind of wording that we saw in the example problem that was given in the problem chart. But now we can also color it, so they actually decide for themselves how they're going to partition the sheep, and then they record their thinking in a number bond. clearly this won't be the first time they've seen a number bond. But on this page, you see two different representations. You see the actual visual representation of sheep, and then you also see a number bond, which is more abstract. So two different representations, and they have to build the number bond based on their work with the more concrete visual representations. And here's another example where they have 6 snap cubes together, and they have to decide how they could be 2 different colors, and from there that's going to generate the 2 different add-ins or parts. In addition to being able to understand that a number, a quantity, can be partitioned into 2 smaller quantities and that supporting standard 2, we also have this idea of how addition and subtraction are connected. So in understanding the nature of addition, the nature of subtraction, how they are different and how they are similar, this work that we do with part-whole relations is really critical to that. This understanding of how addition and subtraction are related begins in kindergarten, but it's really a big idea. So it isn't actually designated as mastery until 1st grade. But that kind of exploration should begin in kindergarten, so we'll talk a little bit about that. They need to understand that addition and subtraction are reversible, and initially they will think of this most often in terms of actions, but the relationship isn't entirely action-oriented. There's a number of problems that have no action. So we need to think about that in terms of how this study of part-whole relations could help us. So let's think back to the sheep, for example. No sheep left and no sheep came. So the idea of subtraction and addition being reversible in that case doesn't appear to make sense. But you can think about it as I can join 4 green sheep and 2 blue sheep to get my set of 6. Or if I know I have 6 sheep and 2 are blue, how many are green? That's the exact same relationship, but no action. So we'll take a look in a minute at what kinds of representations might support that perspective. But the important thing is that children see these relationships in more than one way. They definitely need to use words. Words are very critical here because the words are going to be tied to their sense-making mode. So we're talking in terms of sheep. We don't just point to a numeral and say this 3 is part of 6, but these are the 3 blue sheep and the 3 green sheep, and together all of the sheep are 6 total. So we try to tie the things they're doing in more abstract representations back to the words in the story. Number bonds are very useful. They were actually designed, the number bond graphic that is. A number bond is merely a number relationship, but the number bond graphic that we tend to use was designed to illustrate the relationship between 2 parts in a whole. Tape diagrams, I'm going to show those to you in a minute, are another way of showing that relationship. And then finally, equations. Now, our goal is to really build from where students are already making sense towards the equations. And we're not necessarily going to get there early, but we're going to keep working in that direction incrementally, showing them how to represent their thinking in slightly more abstract forms. Always starting from something they've already learned, already explored, already discovered, and then saying, for that thing that you just did, let's see what it looks like as an equation. Here you see 3 different types of representations. I have 2 of the combinations of 5 here. And in the first diagram, you see the actual number bond, although this number bond could be made a little bit more concrete by actually putting in the dots instead of the numerals. Then you see it as a tape diagram. That's what the middle images are called. And here I see that one green box and 4 red boxes all together is 5 boxes, and that's represented very easily through this visual. And then the final one is the equation format, and you'll notice if you look at it that the total is actually on the left side of the equals sign. The Common Core authors in their progressions document have indicated that for problems like this one, where children are decomposing, they really want teachers to show that decomposition with the total on the left side of the equal sign. And there's several reasons for this. First of all, it makes sense sequentially that you put that where you're starting. I started with 5 and now I'm decomposing. What are the different combinations or expressions that would be equivalent? They really want the focus on the equal sign as being showing something that is equivalent, showing something that is the same as. And so if you put the equal sign always at the end with the total at the very end of the equation, children often develop a misconception that an equal sign is really a signal to compute. And it isn't a signal to compute. It is really a signal of equivalence, a sign that the things that are on either side of this equal sign are equivalent to one another. So they want children, even in kindergarten, to see different formats for the equations. So I mentioned that number bond is a very useful graphic because of the fact that it was designed to show a relationship between two parts and a whole. And here you see how a relationship between two parts and a whole can generate a number of different equation formats. And I've shown the whole in different places so that you can see that. Notice that for addition, the whole can be either first or last. On the subtraction side, notice that even though the whole is in different positions, it is always to the left of the minus sign. That's something that we want children to get as an idea in the first couple of years of school. Now, once they have meaning, really strong meaning for a number bond, they recognize where to position a whole, for example. You can say, here I have a number bond. Tell me, where should I put the total? And they know exactly where it is. They see that the two parts extend out from the whole. And you'll notice that the format, here I have the whole at the top. Here I have the whole off to the left. You can shift it. It can be a box. It can be a circle. Once they have the idea of the relationship and they understand how to use it, they can generate their own. They know what a part is and what the whole is. Then the children are in a position to begin to explore how these look different in additive situations versus subtractive situations. Either late kindergarten, your more advanced learners, or for the masses, perhaps in first grade, children are to develop a more generalized understanding that addition is what you do when you know two parts and you're searching for a whole, and subtraction is what you do when you know a whole and a part and you're missing the other part. And then I have a box around this whole equals part plus part, just to remind you that for decomposing problems, the Common Core authors want us to use that format of putting the total or the whole first. Now, because number bonds are very useful, we want to be extremely intentional so that they have meaning for the students. So very intentional introduction. When we introduce number bonds, we don't just throw a number bond up on a smartboard, for example. It's part of a sequence, concrete to pictorial to abstract, which you see here. So we see the lions, male and female, and we can model. The male lions are being modeled here with 2 red snap cubes and the female with 3 blue. And then how would we find out our lions all together? Well, we could bring those two quantities together. So you see the 5 cubes in the whole. And then we can decide how we could represent those with the symbols we use in math for those quantities. And so that shifts us into the most abstract for this sequence, which is the number bond. Even more abstract from this would be the equation, because there are some added symbols in an equation, as well as some thought about, does the order matter? Which, in addition, perhaps not so much, although it does matter whether you have the whole on the opposite side as your two parts, or if you've mixed it up. So there's definitely some greater levels of abstraction that occur when you get to equations. Here's a warm-up that you can do, and I have this in here just to show you how you can do something that actually takes very little time during down times of the day, but which can reinforce this idea. You can do a concrete pictorial abstract progression pretty quickly. Here you see hiding fingers, and in this case you hold your hand. Notice that this image of a hand shows the typical finger pattern for 2. The Common Core authors have indicated that kindergartners need to be aware of all the finger patterns and be able to tell them at a glance, certainly up through 5 for sure, and you can work on some of the others. But in this case, when I look at it, there's 2. Notice that the view of the hand does not show the other fingers. All you see are 2 fingers. The others are hidden. So that's the view I give to the students, so they can't see my other fingers. But everybody has 5 fingers on the hand, so it's easy to figure out. I have 5 fingers on my hand. I see 2. How many fingers are hiding? Here you've essentially taken 5 and you've partitioned it into a 2 and something else. But they have their own built-in manipulative on the ends of their arms that can help them figure out what the other part is. So once they've done that, then you can write on the board the number bond, and you can also write an equation. Eventually, using number bonds quite frequently, especially in number talks, which we're going to talk about in the next lesson, children get pretty good at them. They get pretty good at being able to identify what the total part is and what the two parts or partner numbers that are embedded in that whole. And so they get to the point, for the most part, where they are able to use these number bonds pretty well if it's emphasized in a regular part of your classroom. So children learn then to actually represent mathematical situations in slightly more abstract forms, first beginning with concrete and then with a number bond as shown here. And they learn to identify within a problem what a total is and what the parts are. So that's really important as they get into even more problem types in first grade. If they have the capacity to kind of analyze a problem and think about what a total is and what the parts are, that is a huge advantage for them. They learn to make number bonds on their own, and they learn how to use a number bond to help them think through how to write an equation. At kindergarten level, this is going to be for the easiest of problem types. And you're going to be okay if they just even get an expression, if they can talk about, like in this case, 3 plus 1. Here you see a child in this image who's doing a task like this, and they have modeled things, and you see the models there. And then they've drawn a number bond, and right below that, if you can see, they are using the number bond to construct equations. Mind you, this is late in the school year, but you work through a whole progression that actually gets to the point where they can do an exercise like that. Here's another tool besides a number bond, another tool for helping students think through part-whole relations. You give them a card that's partitioned in the manner you see here with a target number written at the top. For kids who I need to differentiate, instead of putting the numeral at the top, I would show a visual image of the total quantity. And then they are given counters and they have to decide what are all the different ways I could think of to partition that total into different parts by putting them on opposite sides of this partition barrier. And then you can record them on a chart and they can search for some patterns. I have just a couple of quick instructional ideas. There will be more instructional ideas that are popping up throughout the week as we talk about number talks and then about reinforcement activities. In this particular task, you see that children had been working with combinations that make up 5 and combinations that make up 6. I should point out that this was the end of some explorations. In the case of 5, the children had already been through an activity where they were trying to find all the different ways in which red apples and green apples could be combined in packages of 5. And so they had been through that task, and then afterwards they had already an idea of, thinking about 2 parts making up a whole in the context of apples. And then we brainstormed and kids got 5 stickers and they had to decide how they were going to do it. And then we recorded on this chart. And it started out with me actually doing the expressions that you see there. At this point in time, they had not yet had equations, so we were sticking to expressions. Equations were still on their horizon, but fairly quickly the kids wanted to take over, and so you kind of see through the handwriting that the children pretty much took over by the time we got to combinations that make up 6. Once you have the combinations here, children can study them and think about patterns. For one thing, they might actually notice that 2 and 3 is up there, and also 3 and 2. that 1 and 4 is up there, and also 4 and 1. So one of the patterns that they may begin to notice through studying this actually ties into the commutative property. So that's an example of something that children can actually look at a chart, search for patterns, and come up with some deeper mathematical understandings as a result. The book How Many Snails by Paul Gigante Jr. is also another example. Not the only one, however. There's lots of rich math literature that can be, that lends itself to the use of number bonds and part-whole relationships. In this particular 2-page spread, you see an example with clouds. There are 8 clouds, so that's a number under 10. And if that's appropriate for where your students are in their learning journey, you could do an activity like this with them. And you have 2 number bonds. First of all, I've got even some actual clouds partitioned here, so they can think about them as 4 white clouds and 4 gray clouds, or as 5 small clouds and 3 large clouds. And you can do that with the actual images of the cloud, and with the number bond, and with the equations. It's possible, depending on your class, that you might even be able to show them a situation where they found 2 different ways to make the same number. So 4 plus 4 must be equivalent to 5 plus 3. All right, number bonds grow with the learner. Although what you're about to see is not kindergarten anymore, I wanted to talk about this because last week we discussed the fact that a good representational tool should be able to grow with the learner. And at first glance, you may not see how the number bond can do that. But I wanted to show you some things that include number bonds for older children, so you would see a little bit of how it grows with the learner. This is an image from a 2nd grade textbook where they're learning some strategies for subtracting 98 and 99. And if you were to do this in general, like 203 minus 98, that would be a problem that would involve regrouping. But here they very cleverly avoided that and turned it into something that's so easy they can do it mentally by partitioning the 203 into a 103 and a 100. 100 minus 98 is 2. And I still have the 103, so I can actually calculate that out in my mind as 105 quite easily. That's 2nd grade mental math. 3rd grade mental math is also illustrated here, and I want to just briefly have you look at the mental math for division. This is 4th grade, I believe, and in this case 51 is being partitioned into 30 and 21. Why? Because that problem they were given is 51 divided by 3. So if you can actually quickly generate 2 numbers that are very familiar to you and which you know are divisible by 3, you can break the 51 up into those numbers. So 30 and 21 is an example. I know instantly that 30 divided by 3 is 10 and that 21 divided by 3 is 7. So I can, in my mind, quickly figure out that 3 goes into 51 17 times. Now, if I didn't decompose that, I have to tell you that 51 divided by 3 is not a basic fact. I would have to do it through long division. The number bond illustrates how you can flexibly decompose whole numbers into 2 parts that in a way that allows you to be strategic. There's some more references here. The Lubinsky and Otto article talks a little in much more detail than I was able to go into